All right, now for chapter 2, we need to cover one more approach where under CF control finite control volume FCV, we have covered the conservation of mass where we look at m dot in equal to m dot out, and the second Newton law F equal to ma, and then we convert to mv divided by t. We show the equation to find the forces and also even the torque. Today we're going to look at, and then we look also the last tutorial question, we also look at work and power. There is one tutorial question that show you how to convert all your calculation into work and power. So go and look into it. Then today we're going to look at thermodynamics. We're going to look at energy equation. Okay, first and second law of thermodynamics. This is today's focus. Okay, all right. So today we're going to look at the energy dimension. Today we're going to look at a loss of equation. I'm going to go very fast on the derivation of equation because you can always go back to the PowerPoint slides. Only I want you to pay attention on a few areas. Okay, so let's look at the first law of thermodynamics where you learn in your Thermo 1. Okay, so if you look at the screen here, the first equation you see on the screen is actually quite similar to the one that you learned before this. What is different, what is similar is that you look at control volume dimension and also control surface dimension. The rho and volume still the same. And then the rho v and the a also same. Only the left hand side, what is different is that I want you to recognize or see the differences. Because we are now at the energy dimension, we look at thermodynamics with focus on energy. So the in front one is the energy. Yeah? So here also, this one also energy. Not energy, but it's okay. So this one, yeah. So this is the, we call it hydrostatic energy. Later I will explain what this component in, but you just can see it as the energy also. And we will look at Q dot and W dot, which is your power, and your Q is the mass flow rate in the system. So it's the energy also. This one is your energy. Q is your energy in the system, plus the power, rate of power, or power inside your system. So what is E? E is energy per unit mass. You can, if you want to write in the unit, we call it joule per kilogram. It means you take the mass and divide it by the energy. Divided the energy, and then this one is the energy form, where you learn in your physics class. You know the energy cannot be destroyed, right? So energy normally have a few type of energy that you learn. The first one is kinetic energy, KE, that you learn in your SPM. Kinetic energy equal to half mv squared. Okay, start to recall what is kinetic energy, and then the potential energy. Potential energy linked with gravity. So potential energy always you can calculate mgh. Mass, gravity, and height, mgh. And another one is the potential, not potential, internal energy, which is built inside the atom that you learn from your chemistry class. So, and internal energy usually by a small u, small u. So as you can see, compared to the equation that I write in the yellow here, so the differences is that you already divided the mass inside the equation here. You already remove the m inside here because we are looking at the whole equation divided by mass. All right. Now for the first part of this lecture, we're going to look at this equation. Okay. Just to recognize the structure of the equation. Basically, you're looking at energy. if you look at control volume dimension, you look at E, which is the energy per unit mass. The control surfaces, you look at the energy and times the vector dimension. Q net and W dot shaft, this one I will explain later. Okay, these two things you can see as a power, as your power output. Okay, so we're going to keep repeating energy and power in this session. All right. So the next one, going to go a bit fast for a few more slides, as you can see from the slides here. So there is one concept is that the total energy must always a substitute, not because it's is a summation of heat transfer to the system and work done in the system. One is the heat, one is the work. Okay, the energy in a system consists of the heat and the work inside the system. So the heat and work is the keyword that contribute to the equation above. Okay, so this one, the Q, you can see it as a heat, H, not H lah, but you write as a heat. This one as your work. Okay, now these two is the one that we call it useful energy. Useful energy. What I mean by useful energy means you can use this one to make some devices move, or you can make it to move something or to generate energy and so on. Okay, so first concept for today, the first 5 minutes is that you recognize the equation for the first law of thermodynamics, especially in the energy dimension. It will consist of total energy will equal to what happened in the heat dimension plus the work dimension. So this is the first concept that you recall from your thermodynamic 1, that you combine with the fluid mechanics. All right. Now, once we've done this one, so I'm going to go very fast. So as you can see here, just now we talked about the total energy. We talk about total energy. You can write as integration of your system. Then just now we talk about heat will equal to this one, which is talk about the system. Q minus Q, which is your heat, Q dot, plus the work, which is your W dot. So if you want to calculate the changes of Q or your heat, what you take, you compare what is in and out. Means that is what have changed inside the system. The heat dimension, you take input minus output, you get the changes of your energy. Then you look at the work dimension also. What is in minus what is out on the work dimension. Okay, so we keep repeating the same thing. Energy, look at Q, which is your heat, plus your work, W dot. So we are now dealing with these three, and lock your attention to these three. E equal to Q dot, W dot, means energy equal to heat plus work. So we're going to keep repeating and expanding this equation later on. Okay. Right. Then this E that we see in the beginning, this E is the energy in a unit of mass, which is equal to U plus V squared divided by 2 plus GZ. What does it mean? It means that, as you can see, this actually the energy that we discussed just now, the three types of energy that we see just now. The first one is internal energy. Second one is the kinetic energy. Okay, you have your internal, you have your kinetic and kinetic energy, and the third one you have your potential energy. Okay, okay, mgh. Right, z in this case your h becomes z. Z is the elevation of your position. Okay, so for example, you throw a stone from a cliff. So the potential energy will be considered the elevation from the drop point, which is the Z, or your H that you use in your physics or SPM class. You use H. But for this module, we'll use Z to represent the changes of height, Z. But the concept's still there. Okay. Next, we move on. Mathematic dimension, when you combine the E, combine the H, the heat, Q, and the W, which is your work, you can write your equation as Q plus W in the system. And with the word net, net means you calculate already the differences of Q and the differences of your work. Then you can write Q net plus W dot net. Okay, so still we look at heat and work. Right, so I hope you already imprint the message that we keep repeating the energy. We look at heat and work dimension. Okay, so let's look at this equation where the total energy in the system will equal to your heat plus your work. Then look at Q net. Okay, now when you do analysis, this is the cheat sheet, or there's we call it the guidelines when you do calculation later on. What happens if your energy is go into the system? If your Q or your heat go into your system, or there's a statement mention the heat go into the system, you straight away you write Q dot is is positive. Okay, because you add something to the system. Okay, go into the system means you add energy to the system, you get positive. If you take something, the heat from the system, the heat is taking out, you will get minus Q dot. Okay, positive, negative concept. Now we are at the energy dimension. So when you see a positive Q, it means you add the heat energy inside the system. Normally, when you add heat to the system, the temperature will go up and so on. The most obvious one is the temperature will go up because you add heat. Okay, so if the temperature go down, T drop, meaning you remove heat from the system. Okay, the temperature will drop. So this is the very obvious phenomena that you can see. Okay, now what about the we are going to do something conversion later on because we are now developing the equation. So we can change something in this system equal to control volume dimension when, again, when your, let's say the yellow color is your system, and you fix your control volume around the system. So let's say I draw the red color line. Red color line is your CV, control volume, like what we cover in the previous session. So if your control volume same as your system, then you can convert your calculation for system will equal to what happened to the control volume. This is a mathematics model dimension. When you analyze, when you have this assumption, then you will do something on the equation. it means you can change this system into CV dimension. Okay, so this is the assumption that we did in the mathematics dimension, where later on you will see that we convert this system into CV dimension. Okay, so when there's a equation that you see suddenly the system change to CV, where suddenly in the equation you see system suddenly change to CV, it means that you have this assumption. Means that your CV co-incline, mean match with your system. Okay, the yellow color is your system. All right, I go a bit further. So we already covered the concept why your system can change to CV just now. And recall that your thermodynamic equation just now, that you can derive the energy in a system by looking at the control volume and control surfaces just now. And then this is what we summarize from the previous slides. When you look at net means we already do all the calculation for your Q and W, okay, for your heat and work. Then the next one will be, again, this one is, we still look at non-deforming dimension, and Reynolds transport theorem will be the similar pattern, only the E is changing. The previous one we look at velocity, but when it comes to first law of thermodynamics session or chapter, we change the volume, not volume, we change the velocity into energy, E. Okay, as you can see here, E. Okay, so we combine these three equations, we will reach the first equation that combine what we learned so far. Okay, so the last equation that you see on the screen here is actually a combination of the above three. Okay, now what does it mean? It means that you equal your system equal to CV, and you equal this equation equal to this one. Then you substitute this equation inside here, right? You substitute this one inside here. So you'll get the one that you see on the bottom of your screen. Okay. All right. So this one will equal to CV, will become the right hand side. And the left hand side, the integration of system E rho dV, the volume, will equal to your control volume and the control surfaces. We put on the left hand side. Okay. So you can view back these slides many times after this, right? Okay, so this is the first equation for today. Not first lah, but is a combination or summary of what we're going to use later on. Second concept for today is the Q, which is the heat transfer rate. So as you can see from the diagram here, you see a loss of Q there. The arrow is pointing in and out. Okay, so by recall back what is positive sign and negative sign just now. So if the heat, again, if the heat going in, if the heat is going into the system, mean you add heat, the temperature going to go up, right? So you add energy means it's positive to your Q dot. If you remove, you get negative. Remove, go out, get negative. So you look at this diagram. You have 4 arrows there. So Q dot 1 arrow going in, go in positive. You get positive sign here. You look at 2, Q2 point in positive. You add energy to the system here. So Q2 positive. You look at Q3 arrow pointing out negative. Remove energy from the system. That's why you see a negative there. Q4 also same. Q4 arrow pointing up means you remove heat from the system, negative. So mathematically, you're given a free body diagram like this. You should able to write this equation. The Q net inside the system, Q net in will equal to the total heat energy that happened to the control volume here. You add all the Q dot. All right. So you look at the arrow. If go in positive, come out negative, then you summarize the equation. Okay. So important, you know how to differentiate what is positive or negative. It's quite direct, huh? It's quite direct. So once we cover this one, all right. So another word that you need to recall from your thermodynamics will be adiabatic. Adiabatic means no heat transfer happen. Okay, yeah. So this also another important word when it comes to your exam. So if you see adiabatic process means no heat transfer. No heat transfer mean your Q dot equals 0. Meaning if this is a adiabatic, this diagram over here is adiabatic, then your Q dot net total, Q dot net total will equal 0. Means Q dot 1 plus Q dot 2 minus Q3 minus Q4 will equal 0. Then you can calculate what is your Q1, Q2, even Q3 and Q4. There will be one or two parameter missing that you can calculate from this word. All right, this adiabatic keyword will help you to simplify your equation. Means straight away, if you see adiabatic process, straight away you go to the Q net equation, you put 0. Okay, there's no heat transfer happen. Okay, so this is one of the mathematics equation that you can use. What about the work? The work transfer rate W dot, the work W. If you see W dot or the rate of work, if you take W, your work divided by time, it will become power. Okay, you take work divided by time, you become power. Or mathematic notation for this chapter, we use capital W and a dot above it. So also there's a positive negatives for the power or the work rate transfer, the rate of your work or your power. So if the work is done on the system, okay, let me draw a box here. So let's say this is your system. If you've done something by the fluid particle, let's say you have a loss of air at, let's say oxygen or water vapor molecule here. If this molecule did something to this surface, if this air molecule did something to the wall of this wall here, your W dot will be positive. If your molecule done something on the system, your work will be positive, or you have a positive power. Okay, so you calculate in your final answer, you get W dot positive. It means something means the fluid did something on the wall. You do some work on the wall. Okay. Right. So the same apply for the negative lah. Negative means the work is done by the system, or the work had been taken out from the control volume. You just memorize the positive. All right. Positive means there is work done on the wall. Okay. Next one. We are now looking at work already. We have done with the heat just now. Okay. the heat just now. Heat, positive, negative, already explained by this diagram. Okay, by this diagram, the Q. When is positive, when is negative. Now we look at W, the work or power. So the positive, it means the work is done by on the system. Negative means the work done on the fluid. Okay, so try to differentiate the positive, negative. Positive means on the system. Negative means on the fluid. Okay. The target is different. Huh? Positive means something happened to the system. Negative means something happened to the fluid. Okay. All right. Now, what can the power equation can use in several conditions? First, we look at shaft. What mean by shaft? So, for example, you have a boat, right? You have the boat, and you have a motor here, and motor have a shaft that link to the propeller. Okay, so this shaft must be do something. There's a work done by this shaft that turn the propeller. Okay, so we're looking at the work done by the shaft by using thermodynamic law. All right. So what can this equation can be used? So the first equation, every time you see the keyword, calculate the work done, the work rate, work transfer rate or W or power. Calculate the power for the moving shaft. The equation that you use is the one that you see on the screen here. Power of the shaft or W dot equal to T torque of the shaft times the omega. Okay, we already explained what is torque in our previous lecture. So let's say you have a reference plane and there's a point of interest and you have a force along the plane there. Let's say you have a force and you have a distance, which is a d. This is what you learned in your physics class. So if the distance is perpendicular, then the rotation or the torque action done as a result of this force will create clockwise direction of torque or T. Okay, so this is how you convert the force and the distance, or we call it arm of the force. So the products that we already cover by using your right hand rules. Huh? The right hand rules, when you close your fist, the direction of the torque, the T represent by your thumb, and the four fingers will represent the direction of your rotation. Okay. Okay. So the power equation, when you solve question, I especially ask you to solve moving shaft, you use this equation. T times the omega means rotation speed. Omega is the rotational speed, usually in the unit of radian per second, or RPM, revolution per minute. Here you need to recall how to convert 360 revolution to radian. 360 equal to 2 pi radian. So you need to convert from revolution to radian per second. Okay, because one revolution means one cycle equal to 360 degree. 360 equal to 2 pi radian. So you convert how many revolution per minute. So 1 minute 60 seconds you convert. Okay. All right. So if you are considering more than one shaft, how you modify the equation above means if you have more than one shaft, you take the input minus the output. Okay, you calculate all the shaft work minus all the net. You can say as you calculate the net of the work done or the power. Okay, so this is how you do it when you calculate have more than one shaft. We'll look at one example later on. So far we try to cover the theory first. Then once you understand the logic behind, then you can you can solve the question accordingly. Okay. The first way where your power can be done, we already cover the moving shaft. Second method, second example, work. You convert the rate of work, W divided by T, get power. First example of power, we'll be looking at the case of a moving shaft. If a moving shaft, you use this equation. If you have more than one shaft, you use this equation. Means you calculate the shaft input minus shaft output, input and output. Okay. For example, let's say you have 2 engine shaft. Okay, you have 2 engine propeller. Okay, you need to calculate the total work done by the shaft. So how you calculate? You calculate the in for the first one, in for the second one. Okay, then minus output of the first one minus output of the second one. Then you get the total power of the system. Okay. Second example, after we look at moving shaft, second example will be on force or pressure, water pressure. Oops. On the pressure, we know that pressure equal to force divided by area. Okay, force divided by area. In this case, we'll use the equation of stress, because stress also force divided by area. Okay. So something interesting about the equation is that there's a negative sign in front of the forces. Why? It is because, okay, before I explain the negative sign, you need to recall the understanding in your static class. What mean by stress? Stress, when you have an area of a cylinder and the force is normal to the area. I'm not sure whether you can see the color. Let me change another one. If the force is 90 degrees to the area here with a force, okay, this one is your area. So when you want to calculate the stress, the normal stress on the area, normal means 90 degrees, the force is 90 degrees to the area. You take your normal force divided by area, you get stress. Okay. Now, if you look at the normal pressure and the normal stress working on the pipe, for example. Okay. So the way of the pressure act. Okay. The above one is the force. The second one is the pressure. We already covered the concept of pressure. So pressure always act normal to the surface here. Always 90 degrees, the pressure. But it was always go in or acting on the surface. Means the arrow will always pointing to the surface. So if you compare the two diagrams that I draw, the magnitude will be the same. Means you can convert pressure to forces and area. All right. F divided by A is pressure. Only the direction is different. The way they act is different. So if you this means that you can convert pressure into stress. Okay, this is stress. If you take F divided by area, you get stress. Normal stress, especially, right? Why normal stress? Is just to strengthen the description that the force is 90 degrees to the area. Okay, so if you compare side by side, what you can write mathematically is that stress equal to negative P because of the different direction of arrow. Stress always going out, pressure always going in to the surface or to the area. Okay, so that's why you explain. You can write stress equal to negative P. Okay, yeah. Repeat this video later on to understand why suddenly there's a negative in front of the P by referring to this diagram that I draw. Okay, or you can stop me now if you don't understand why suddenly there's a negative sign there. I think it's quite clear enough from the diagram that I draw. Okay, so that's why we can write stress equal to negative P. Okay, so we substitute by the second scenario, we look at force and stress. So there's a vector diagram, especially when you deal with force and velocity. As you can look at the diagram on the left-hand side of your screen, all right? So if you move something at a certain velocity with a force, you can describe the phenomena as power. Okay, if you move something, an object with a velocity and a force, you will get power, or the rate of change of your work, or W divided by T, or power in short. Okay, recall this also you learn in your dynamic class, right? When you learn about power. So W dot equal to F dot V. However, we can when you talk about dot, right? Today we need to recall the dot products. When you talk about dot, the two arrow must go together. Okay, dot products, the force arrow and velocity arrow must go side by side to produce power. Okay, this is an important concept. Once you understand this one, you can understand the rest. Okay, when you talk about power, you look at force and velocity, and you are using dot product, not cross product, not this one. We are using dot products to calculate the power. So what kind of scenario that force and velocity will generate power, or there's a value as a dot product, is when the force is parallel to the direction of your velocity, then you generate power. So if you look at the screen on the left hand side here, the diagram, to make the arrow of the force parallel to the velocity here, what you did is you use a trigonometry equation, theta. The one that relate here and here is cos theta, right? Is cos theta. So you are converting the force into the velocity dimension. Okay, I'm drawing the diagram one more time. This is your force. This is your velocity. Again, to make the effect of force times V to get the power, both must be in the same direction to get power. So you learn from your mathematics again. You expand the force to two directions. One is this direction. One is this direction. So this direction gives you F with a theta. This is F cos theta, F sine theta. Okay, the one that generate power is the force cos theta times V. However, F sine theta, if you dot product V, you get 0. There's no power in this direction. Okay, so spend some time to study this diagram, this important concept. important you memorize 2 arrow going parallel. Then you can get power. All right. Once you understand this one, you can go further. So if you're looking at single fluid particles only, means only one particle, you use the partial differential equation, means there's a delta symbol here, your work or your power, right? Work over time means power, W dot means power of your normal stress will equal to force dot V, force times the velocity. Then you get power. So you can further expand because normally force is not that direct. How you get force from stress? Again, you recall the stress equation. Stress equal to force divided by area. You want to write in the stress dimension. So force will equal to stress area. So that's why you see I purposely highlight this one to white color to show you that the stress is having a vector form. Stress vector times A, but the concept is from the one that I write here. Force equal to stress times area and the volume, not volume, velocity. Okay, so again, this is the, if you times the, this is the equation when you look at single fluid particles. And you can convert the stress into the negative P like what we explained just now. So the final equation to generate power for single fluid, you use this equation, minus P and delta A dot V. If you want to calculate the overall system, what you did is that you, okay, I pull the V to the, beside the P, I will get minus PV dot N delta A. So again, you see the partial differential means single particles. So you want to look at the overall system. What you did is you use the integration procedure to find the overall power. So that's why, as you can see on the screen here, we change the partial differential delta dimension to integration. So integration of your control surfaces. Now just get a bit attention to the power. Power, when you convert power, power only interested in control surfaces, not in the control volume dimension. Okay, power only interested because power, how you generate power is because of your force and pressure. So force and pressure always act on the area. So all the control surfaces. Okay, so that's why your integration is based on the control surfaces, delta A, okay, or dA. So far, we're still looking at mathematics dimension. Okay, so, and you can swap between the stress and the pressure again. Okay, if you use pressure, make sure you carry the negative. If you use stress, it becomes positive. And these two equations give you how to calculate the flow work. The flow, how the flow work inside the system. Then you use these two equations. All right. And the rest you can read from my slides here. This is just a further explanation of the tangential stress. Tangential stress means you see the red color dot here. Tangential means it go 90 degree to the axis here. You see the V and the red direction is 90 degree or normal to 90 degree. So if you have a tangential stress, the power will be zero, like what I explained just now. Huh? So just now, if you convert your force sine theta times the V like this, then you will not get anything. It will be zero. Okay. Okay, let me see. a few more slides. So the rest is just that you combine what we learned so far from the shaft, from the shaft example, the first example. You can not reduce, but you can rewrite the whole thermodynamic equation to the one that you see at bottom of the screen here. Okay, so control volume dimension plus control surfaces dimension will equal to heat. I apologize for my writing. This is heat, work. Okay, so work, you have shaft, and then why there's a negative? Because you are using pressure. Okay, pressure on the control surfaces. All right, then the rest you read from the screen. You rearrange, you get a new equation. And you compare side by side with the one that I write in the white color here. So you compare side by side, you can write the equation in the U P divided by rho V squared 2 plus ZZ. And then the rest will be the same. This is the energy equation, which is important when you study about thermodynamics law. Okay, so we will return to this equation later on. We go for a short break. So we will stop at energy equation here. Then we will continue after 10 minutes breaks. Okay, so this is the equation that we are focusing on. Because just now we explained what is E already. E you substitute inside here. You get this one. Okay. Right, we stop here. We go for 10 minutes break.